Hi, I'm Meir Toledano. I'm data scientist at Anodot, which is a startup company located in Israel, and we also have offices in California. And today I will discuss with you about real-time anomaly, especially in the case for time series. And the major problem we have is with the scale, so I will focus on the problem of scale. So first, what is the problem we have? Did you already try to order a cab during the rain? It's extremely difficult. And why? Because in fact, in the point of view of the application, there is lots of person that are monitoring in real time what's going on during the operation, especially during the rain. In fact, they are monitoring lots of data. It can be millions of time series, which is sampled every minute. So it's a huge amount of data. And in this quantity of data, we need to find an anomaly. Okay, in this specific case, during the rain, there is an increase, for instance, of the wait time. And this is the anomaly in time series. This is an example, very simple example that everyone can understand. But in fact, we can use the tool of anomaly detection in time series in huge of different domains, and especially in finance, we can imagine we're already working in it, as for transaction fraud detection, for instance, or we're also working to monitor the loan acceptance process to check if there is no bug, for instance, an increasement of the rate of acceptance rate of loans. And we can also working on an experiment to transform all the ledger of a company to a time series and then to detect an anomaly in the accounting system of the company, which is most of the time need to be investigated. So this is our pipeline. So this is also our point of view of the problem. So the first point, it's an engineering question, is how to collect such a quantity of data. So this is mainly in engineering. The second part, we are working to model what is the normal behavior. This will be my focus of my presentation today. And after, from this, we also have modeling, an abnormal behavior modeling in order to compute a score of an anomaly to discriminate what is an important anomaly, what is a not important anomaly. And the fourth part is, in fact, is transformed in mainly all the first part of the models. It's univariate time series model. So we are only seeing a time series itself alone. And in the fourth step, we are computing a model which is linking all the time series of one client to extract a relevant business problem. And at the end, the client gives us a feedback which is good or not, and we are also integrated in our model. So as I said, I will focus on the normal behavior of the normal behavioral learning. So first, what is anomaly detection for us? Anomaly detection, it's a question mainly of business. What to find an incident in an industrial process or a business process. So we have at the beginning, the input data is the time series, and we are computing the normal behavior is to compute for us. It's to compute the next point or the end hop, the end point ahead. Conditional prediction. What does it mean? The abnormal behavior, it's for us it's something unexpected. So we are modeling the data, we are modeling the time series. This is what you are seeing in blue. This is the blue area, which is the normal range, which is based on a time series model, and which is far from the model. So which is far from the model, we are defining as an anomaly. So the definition of an anomaly, it's a negative definition. It is something that we don't know, which is not normal. We can also adopt an opposite point of view, which is a positive, and then we need to define a list of possible anomaly and then to detect it. So basically, the problem of anomaly detection, in the math point of view, it's time series modeling, conditional prediction, so given all the past, what will be the next point, and then to compute the p-value, so the probability for the next point. So this is rely on the two standard legs of machine learning, which is the learning, which is time series modeling, and then the inference, which is the real-time prediction calculation. But in our cases, in the case of time series modeling, there is a small point. It is a key point, but it's probably one of the most important points in time series modeling. It's the modeling of season. So for here, I just pick an example. Since our system is completely real time, so you can see with the red line, which is the update of the model. What is the difference before the model is without knowing there is daily season, and after? This is, we identify the daily season pattern, and we can see that the prediction is far more accurate. And in fact, we can even think that without identifying the season, without taking account of this, in fact, it's very hard to make an accurate anomaly detection system. So, I said that we need to find a model from time series. So we choose at Anodot to use the ARIMA model. I will explain why before we need to why, but just I want to recall some basics of ARIMA model. So ARIMA model is it's very famous model of time series, and it's based on, it's mainly to model the dependency of the data, the history of the data, the past data, in a linear manner. It's extremely easy. So you can see, for instance, that the value xt is depending on xt minus 1, and xt we can add all the lag we want. We also need to add the prediction error, which is the epsilon here, epsilon t minus 1, and I also added for the generality cases, I added the xt minus s. So if the time series is seasonal, we need to take account not only the data which are several points before, but also the data which is before in the season. So it can be 1 week before, 1 month before. And this is the basic of the ARIMA model, which is the variant of ARIMA, which is called seasonal ARIMA. The standard, this is technique, it's widely used, and I just want to recall you how to estimate the problem, which is the key point for us. The key point is rely on the maximum likelihood estimation. So there is two legs. First, we need to compute the likelihood, which is mainly the probability of seeing what you are seeing according to a model. And this function will be optimized and in order to compute these parameters. So the parameter here in the model, this is the phi1, phi p, phi s, etc., and also theta 1 until theta q, and etc. So this is the unknown parameter of the model we need to estimate. So I also, in order to be clear, and also I want to add the definition, what is the R? R, it's mainly the size of the model. Okay, if the model is not seasonal, okay, R is more or less the order of magnitude of 3, 4, something very small. If the model is seasonal, R can be very, very big, and it's more or less the order of magnitude of the season. So, for instance, in our cases in Anodot, it can be up to 10,000. So, why we choose to work with ARIMA model? In fact, there is a theorem which tells us that it's the best linear model. So it's great. This is the best one. We are very, but the big problem is the estimation of seasonal model is extremely slow because in fact because of this R. So we discovered that we need to break the state of the art in order to work in our scale. So I just pick several results that we reach. In bold, this is the state of the art. This is the standard R algorithm. If you are typing ARIMA model in R, this is the computation we have. So it will work more or less well for small models, and R will even refuse to start computing for model that the season is more than 150 points. So this is clearly not our cases. And more of that, there is a huge problem of performance. And for instance, at the beginning, the first try was around 10 minutes per time series, and we have dozens of millions of time series in Anodot. So it's clearly undoable. The standard implementation is clearly undoable. So we invest lots of efforts and lots of time to reduce this time. All the different steps, it's a new mathematical technique we use to reduce the time. I won't dig into only the last one, which is one of them, which finished the task. Let's say like this. And in fact, it's the idea that we learn the parameter of the seasonal model and the model of not seasonal model, which is the low and the fast dynamic of the model separately, uncoupled. We are assuming that we are uncoupled the system, and then the learning is extremely fast. This is the key idea. How to do this? We develop a mathematical theory of downsampling. What's going on if we are downsampling the data, and what will be the output of the model. So this is the main key of the idea. At the end, we reach. This is a huge improvement of performance, and this is clearly the wow measure. So this is an improvement of more than 5 orders of magnitude. So clearly, it's turned to be impossible to do at our scale to clearly possible and even cheap. So this is the basic of the idea of the learning with the anomaly detection in time series. Just Anodot in few words, just to understand our scale. So we are processing almost 6 billion of data points every day. So it's a huge quantity of data, which represent almost more than 100 million of time series. We are computing several times a week a model for each time series, which is huge. And as I say, in fact, the seasonal model, it's very difficult, but we have only 10-15% of our metrics is seasonal. It's a small part of our data set, but this is the most important time series are seasonal. So in terms of value for customer, this is not representative of the quantity. And we have also lots of different algorithms, especially I also talk about the correlation between grouping anomalies. We have half a billion correlation every week. So this is the sample of our customer that trust us, and I hope this will growing. Thank you for your attention. If you have any question, we'll be glad to answer.